now let's look at, we're shifting a little and we're going to be looking at ions and their electron configurations. So if we look at N3 minus, well, that's going to gain 3 electrons. They're going to go, according to the Aufbau principle, into the p orbital. Oxygen, again, it's going to get 2 more electrons. They'll go into the 2p orbital. We'll get 2 1s, 2 2s, 6 2p. Fluorine, if we add 1 electron again, it'll be in the that 1 additional 2p electron to get 6 2p electrons. Neon, neon has this electron configuration. Then we start looking at, what about sodium? We remember sodium plus 1 a lot. Well, that'll drop down to lose its 3s electron. That's the one that'll come off because it's in n equals 3. It's bound less tightly than the others. Magnesium, we recall that it likes to lose 2 electrons from the ionic, you're remembering ionic solids. And so those are going to be, again, the 3s electrons. And aluminum, and remember aluminum oxide, yeah, you have Al3 with 3 plus, and so it has a tendency to lose exactly the n equals 3. And as you've noticed a pattern here, if we look at the common ions, all of them are going to have the same noble gas configuration as neon. That's a particularly stable atomic configuration. So it's not surprising that you have things that are on the right of the periodic table that are gaining electrons to get up to the noble gas configuration, and if they're on the left, losing electrons to drop down to the noble gas configuration. Because when you have the tug of war, then things like oxygen are going to want to gain electrons, sodium, magnesium are going to want to lose electrons, and they'll all be happier once they've exchanged them, and they all get to have noble gas configurations, which are nice and stable. Metal ion configurations are a bit different than atoms. If we have iron, Fe plus, here, what are we going to do? We're going to take off the 4 electrons. So Fe plus, we take off the one of the 4s electrons. Fe2 plus, we go down to, we take off all of the 4s electrons. We're down to 3d6. Fe3 plus, which is a relatively stable ion as well, then we take off, we only have 3d electrons left in, outside that are valence electrons, so we take that one off as well. The 4s come off before the 3d. We're removing just 1 electron rather than removing 1 electron and 1 proton. Same things happens, yeah, this is exactly what I just described on the previous slide. The 5s come off before the 4d, even though silver has as a neutral electron configuration 5s1, 4d10. Yeah, so general principle, they go, the 4s, 5s, 6s go on before 3d, 4d, 5d4 neutral atoms when adding 1 proton and 1 electron, but they come off before the 3d, 4d, 5d for ions when taking off 1 electron at a time, leaving the number of protons the same.